Um, Today we'll finish the second part of the carbohydrate, and we will go over the chiral characteristics of carbohydrate, and we will look at some of the chemical reaction as well, and application of the carbohydrates. So let's start with the first topic, which is the chiral characteristics of the carbohydrates. Well, let's define first what we mean by chiral carbon atoms. The chiral carbon atoms are designated or classified to be chiral when they have 4 different groups around them. So we have, this is here, one group, 4 groups. They have those groups here to be what? Different. So now we have 4 different groups. So this is here carbon called chiral, and is given the asterisk here, always with the asterisk like this. So it's given asterisk on the top of it to designate it that this is a chiral carbon atom. And now if we put a mirror here, this is a mirror here. So here it is, here it is a mirror. And then we'll see inside the mirror the same molecule, but a little bit different, with different orientation. We'll talk about this, the unique thing about chiral carbon, that they result or yield to a structure that's not superimposed. Correct? Not superimposed to each other. These images are not superimposed to each other if we have a mirror here. So if you take the left side molecule, which is L-glyceride, and put it on the top of this D-glyceride, because inside the mirror, you will see the D-glyceride aldehyde. Glyceraldehyde L, D-glyceraldehyde. So they are, when you take the left on the right and put them together, you will not get superimposed structure. Correct? And this is typical chiral carbon atoms. Correct? So, and don't forget, that's always, we give them an asterisk. Anytime I have a chiral carbon, I put an asterisk on the top to designate it. This is a chiral atom, and it can yield non-superimposed each other images of the same structure. And this is characteristics for the carbohydrate. Let's look further. Here is an example here. We have here, as I said, here's the mirror. The same molecule we discussed about it. This is L, glyceraldehyde. If you put it on the top of the D-glyceraldehyde, you will not get superimposed structures. The same thing with here, like the hand, chiral objects. If you put your hand in front of mirror, you will see your right hand inside the mirror. And if you take the left one here and put it on the top of this, you see, you will not get any superimposed. You see here, this finger, the thumb is not with the thumb, the other side. So they are not superimposed. So this is the characteristics of a chiral atom, that it yields the structure of, or images or structures of non-superimposed each other. And those two, the L and the D-glyceraldehyde, are called stereoisomers. So those are called what? Stereoisomers. So if you look at this, those both, this one and this one here, is called stereoisomers. Okay, so let's go further and look at the example. Now, if we know what chiral atom is, how about achiral atom? Well, achiral carbon atom, this has four groups, but not with similar groups with each other. So chiral means they are really superimpose each other. So if I take this bottle here at the left and put it on the inside the mirror, the right hand, the right structure here, and you'll get very nice superimposed. You cannot differentiate between those two bottles, correct? And this is characteristic for achiral. Achiral object means a with the achiral means non-chiral, or not chiral means they are not making stereoisomers. So those are no stereoisomers here. Yeah, those are not not chiral. Now, what we call this one here, those stereoisomers, we call them enantiomers. So we call them what? Enantiomers, and this is very good. So now, again, let me just recap whatever I told you. This is what you are doing here. If you have a carbon atom that's 4 different groups, not identical, 4 different groups, this will yield another structure, another image, which is not superimposed to the original image, which those called stereoisomers, and the specific name for this, we call it enantiomers. So if you look at this, those two here, those two L and the D glycerolaldehyde, called what? Called enantiomers. And those, both of them are stereoisomers, but they have specific name. They are image not superimposed to each other, and they're called enantiomers. Now we have another type of stereoisomers, ibimers. Ibimers, you'll see the unique about them. They have different, the hydroxy group at the carbon will be at different location. Might be the same molecule, but another molecule look identical to it, but the hydroxy group can be at the top or the bottom, or we call it in top at the bottom if we have Haworth cyclic structure, or if we have a Fischer, we have left and right. So let's look at some of the examples of the ibimers. Look at this. This is carbon 2, correct? That's a carbonyl group. That's carbon 1. This is carbon 2, correct? And this is mannose. All of those, they have 6. Because the name is changing because of the carbon. So carbon 2, you see? And here is carbon 2. So those here, those called ibimers. Why? Because at the carbon 2, the OH is at the right, correct? So here it is. The OH is on the right, and here is the OH in the left, and here is the OH in the left, in the right. So now, if you look at those two compared to the galactose, correct? Galactose is not isomer with both, but yes, I mean at carbon 2. But if you look at carbon 4, okay, so look at this carbon 4 here, and look at the carbon 4 here, and look at carbon 4 here. Now what you can tell, this the OH at the galactose number 4 is up. So the left side is up. This is left side. This is right side. Sorry. This is I'm trying to draw it, but anyway, you get the idea. This is the right side. Now, if you look at the left, the OH in the left here. Okay, so in the left here, but here here we have it. We have it in the here on the right side. So, and here we have it in the right side, means at the bottom side. So both D-glucose and D-mannose are isomer to galactose at 4. And glucose and mannose is isomer at carbon 2. So the OH at the right is means if you do it in the if you draw it in Haworth, will be at the bottom of the cyclic structure, and the left will be at the upside of this one here. So you get the idea. Isomers is just differing in the position of the OH, whether it is left or right of certain carbon numbers. And you'll see all of those are D. If you look at this, this is D, this is D, and this is D. The mannose, glucose, and galactose are D because of the fact that's the last isomer, the last chiral carbon atom. It has at the right, which is at the bottom. This is at the right, means at the bottom in Haworth, and this is at the right. So all of them D, they have the isomer. Okay. Now we have another one beside now we have two so far. We have the isomers and enantiomers, correct? Enantiomers, that's not superimposed to each other. Isomers, the hydroxy group at certain carbon number, they differ up or down or left or right. And now we have anomers. Anomers is nothing less than the carbonyl group or the aldehyde group. They will have attached to it is OH. If the OH is the bottom, this is an alpha, correct? Is the OH up, this is beta, correct? And remember, this is still alpha D glucose. Why D glucose? We said the last OH, which is the last OH is here at the bottom. So at the bottom means at the right, correct? And this is the last OH when you write it in the non-cyclic, in Fischer non-cyclic structure. So this is for the D. This is for the D, and this is for the D again here. This is for the D, and those are the OH up, correct? Look at this again. The OH up is beta, the OH down, this is alpha. Now look at the how to make the Fischer structure of a carbohydrate. Well, it turns out to be you start with the wedge dash structure, correct? So you start with this here, flip it, rotate it, correct? And then you'll get, when you rotate the whole thing, correct? This one will be this way here. If you rotate, this one will be up, and this one will be go down. This one here is your up, and this one will be your down. So okay guys, so that's the how you make the monosaccharides Fischer projection, non-cyclic. So now here's another example. So just you need to rotate. This is, I will go and rotate this one here up, and this one from the rotation will come down. And you can see this is your up here, and this is your down here. So you see here. So you make you start with the wedge dash structure, you make a Fischer projection or Fischer structure, non-cyclic Fischer structure of the carbohydrate. We'll go further, and you can now know that you can take further Fischer, which is non-stable structure of the carbohydrate. make a cyclic one, which is a more stable one. And you can do this by, you look at the whole thing here. So number 5 here, this is the 5 and number 1. You rotate the whole thing like this. Okay, you flip it this way. And the 5 will be here. And the 1 is here. And then you connect through the carbonyl. Here it is. This is the oxygen here. See, the oxygen of the aldehyde group is here and is connected with through this, and you connect the 5, carbon number 5 with carbon number 1 of the aldehyde group through the oxygen of the aldehyde group, and you make a cyclic, a very nice cyclic stable compound called Haworth structure or Haworth production. And note here, by doing this, the OH here, look at the OH here, OH at the bottom, correct? And the bottom, it has to be alpha. So if I have alpha, I can have OH up, then will be a beta D glucose, according to the Haworth projection or structure. Now we'll go to something else. We'll go to look at the chemical reactions of the carbohydrates, monosaccharides, disaccharides, polysaccharides. So one of the unique natural synthesis of the carbohydrates they are made by plants, correct? Through the photosynthesis process. So the plants, they take this, they take the CO2, correct? And they get the water from the soil, energy from the sun, and they're producing here, they are producing the carbohydrate, which the carbohydrate is here, and they give us oxygen. And this is really a cycle, not only producing the carbohydrate, which is the most important nutrition for the plants themselves, but we are keeping with this oxygen cycle going, because oxygen is produced from the plants, and it's very important to have trees all over the world to keep the balance of oxygen constant. Now, this is just how the carbohydrate naturally is formed. Now, if you look at the chemical reaction of this carbohydrate in the very basic unit and a very important unit, which is contribute to many structures of the carbohydrates in nature, glucose. Glucose can go many reactions. As you can see here, one of those reactions here can react with the hydrocyanic acid. This is hydrocyanic acid here. And it produces a cyanohydrin. And it can go mild, I say mild, oxidation in presence of bromine and H2O as a catalyst. You get gluconic acid. It can go another mild oxidation with diluted nitric acid. You get glucaric acid. It can go, you can heat it, not that much heated in presence of HI. You can make hexane. You can let it react with excess of acetic acid anhydride in presence of pyridine. You get a pentaacetate. You can reduce it further. So in this side, the right side is oxidation, and this side is reduction. So reduction with sodium boron tetrahydride, you get first sorbitol, and if you work on the sorbitol with excess acetic acid anhydride and pyridine, you get hexaacetate. You can see bunch of reaction this is glucose can undergo, correct? Under mild conditions. Now let's look at the hydrolysis. Oh, let's go back first. I said mild oxidation every time. Now, if I use the very extreme oxidation, glucose will decompose according to the combustion reaction, and I will get out of it CO2 and H2O and energy. So this is a typical combustion reaction if you have, and that's not mild, that's a very extreme conditions for the glucose, and glucose will be decomposed and combusted into CO2 and H2O and energy. Nothing will be out of it there. So you can see. But if you oxidize it mildly, you can get different acids out of it. So now let's look at hydrolysis. It looks like in the presence of hydrolysis and catalyst, the monosaccharides, look at this. Monosaccharides will give you no reaction. Here it is. Will give you no reaction. The monosaccharide are not being hydrolyzed. The disaccharides, they are hydrolyzed with H2O. They give you what? Because di means two, they give you 2 molecules of monosaccharides. The polysaccharides, because they are polysaccharides, plenty of them, they are hydrolyzed with H2O. They give you too many molecules of monosaccharides. And this is very important to know of the hydrolysis. Monosaccharide is not. So the glucose, you put the glucose in H2O, there is no reaction. Just solubility will be dissolved, yes, because of the hydrogen bonds, correct? But reaction, no, it will be not hydrolyzed. But disaccharides, yes, you break the bond between the two saccharides, the 2 molecules of carbohydrates, you make 2 separate identities of carbohydrates molecules. We talked about the combustion reaction. That's another time. We talked about it already. And you produce CO2. You produce CO2, H2O, and energy, correct? And that's, of course, very extreme, under very extreme conditions. Oxidation of reaction of using an oxidizing agent. Well, go back and look at the aldehydes and ketones modules, and you will see if you oxidize aldehydes, what you get? You get carboxylic acid, correct? And if you look at the ketones, if you oxidize ketones, we told you oxidation of normal ketones, there will be no reaction. That's true. But the carbohydrate is a special what? Special ketones. And therefore you can let them react with a mild oxidizing agent. And you get, with this case, carboxylic acid. This is, again, this exception for the rule. Normal ketones will not do that. There will be no reaction. However, the carbohydrate with the ketones here, look at this, there will be reaction because of the fact that you have too many hydroxy groups, so they can interact with the oxidizing agent. Now, the unique thing, and you have to really to understand this, and this is very important here. Here it is. Sucrose will give you no reaction here. So sucrose with oxidizing agent will give you no reaction. That's very important. Why sucrose is not, while all the other carbohydrates are being oxidized and they give you the corresponding carboxylic acid, except sucrose? There's no carboxylic acid. Well, it turns out to be there is no free carbonyl group that can be oxidized, aldehyde or ketone into the corresponding carboxylic acid. Therefore, there will be no reaction at all with the oxidizing agent, with sucrose. There is no free carbonyl group. Make sure that you make a note of this. There is no free carbonyl group available in sucrose. Everything is tied up in the 2 rings together. Okay, so now let's look at another reaction. Now reduction. We went to the oxidation. We get to carboxylic acid, or corresponding carboxylic acid. How about if you use this one here, which is a sodium boron tetrahydride? This is a very good reducing agent. And you have here a ketone or aldehyde, okay? So then if you reduce the carbohydrates with the keto group or aldehyde group, so you will get 2 things. So if you have a keto group, this is a keto group, you get secondary alcohol. And that's what we did in a normal 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 ketone, correct? And if you get you know, if you get the aldehyde group, you get primary alcohol. So this is primary alcohol here, okay, and this is secondary alcohol. So the reduction, again, let me repeat, the reduction of carbohydrates, if they are keto carbohydrates, will yield secondary alcohol. If they are aldehyde carbohydrates, they will yield primary alcohol as the same normal conditions or normal reactions with the real normal ketone and aldehyde. So now we have here very unique stuff here. Formation of hemiacetal and hemiketal. What's happened is if you have a carbohydrate with the aldehyde group or ketone group, so and you put one molecule of alcohol in presence of an acid here, catalyst, you get this structure here. So this structure is unique. It has one OR and one OH. This called hemiacetal. If I have two ORs, meaning I have to add here two molecules, then I will have to take this one out, and just as this is an acetal or ketal. That will come in the next slides. Yes, look at the next slides. If I have here two molecules of OH with the carbohydrate with the aldehyde group or keto group and presence of an acid here as a catalyst, so I get how many? Two ORs. This is called acetal or ketal. Let's look at the examples here. I might have to be apologized because I have to blow it up so you can see it much better. So yeah, so I'm blowing it up so you can see it much better. Yeah. So now here we have a D-glucose, correct? And this is a Fischer, and I want to make Haworth, so I have connect this one here with number 1 with number 5, correct? So connect them here, see here, through what? Through the oxygen here, through this oxygen. Okay, so now I have, this is number 1, this is number 5, and this is the oxygen here. You can see the oxygen here of this. Let me just take out of this. Here is the oxygen. Okay, connected, and then I get this very nice Haworth structure of cyclic of the cyclic. We started with glucose and we produced glucobironase. So you can see how nice you can connect them together and you can produce a cyclic compound. Now look at this very closely here. I have here one OH, correct? And this OH is up. So this is beta, correct? This is, here it is. This is beta. I can make it bigger so you can see it here. I apologize. So this is, can you see it? This is beta because the OH is up. Now, make sure that you understand this is the oxygen here, okay, with the rest of the molecule here. This is OR. This is OR. OR. So this is an hemiacetal because this carbon here, and this is always connected to this carbon. This carbon connected to OH, and the whole molecule is OR and the H. So therefore, and the other group. So therefore, this is a hemiacetal, correct? Acetal. Why? Because it started with with the aldehyde group. If you started with the keto group, then will be a hemiketal. So let me go down a little bit. Okay, so now here's the same thing here. You start with fructose. Now here, let me again, I want to blow it up a little bit so you can follow me much better. So look at this one here. This is a fructose, correct? The fructose is a keto. It has what? Sorry. Here it is. This is a ketone group, keto group, carbonyl group, and this is a fructose. This is a Fischer non-cyclic structure or projection. Now I want to make this one here a cyclic one, correct? I connect number 2, as you see, with, if you look at this, number 2 with number 5. So number 2 and number 5 is connected. Here it is. And if you look at the number 5 here, connected to number 2, and the OH will come out, see here. And you get, can you see it? You get a 5-member ring, and the OH at the bottom, correct? The OH at the bottom, and the OH at the bottom, this is an alpha. Now, this is another OR here. The rest of the molecule is OR. So this is hemiketal. Hemi what? Ketal. Why ketal? Because it starts from the keto group. This is a hemiketal, and this is what it says, hemiketal. Okay? Let me just bring it back again to this normal. Okay, so now the last thing here about this project, let me check. Here's the secondary possibility that you can make out of this fructose. You can let number 6. Here we did 5, correct? You can here do 6 connected to 2. So 6 to 2. So when doing this, 6 carbon 6 connected to 2, you get the same thing here. The OH is the bottom, that's alpha, but you get different, you get 6-member ring out fructose. So fructose can have 5-member ring and 6-member rings, and both are hemiketal. Why? Because you have this number 1 here connected to the OH at the bottom and the OR of the molecule. Okay, last topic here, we just go through the application of the carbohydrates in our food. You will see the good carbohydrates in general has to have low or moderate calories, as you see, high in nutrition, and less sodium, high content in fibers, and less amount of saturated fats and cholesterols. That's the requirement for good carbohydrates. The bad one will have the opposite. They will have a high amount of sodium, high amount of cholesterol, high amount of low amount of fibers, low amount of nutrients, and a high amount of saturated fat. You can see the real life carbohydrate can be in our food, and you can see maltose can be found in honey, maltose can be found in molasses, amylose can be found in potatoes, lactose can be found in milk, glucose can be found in many fruits, and sucrose can be found in sugar cane and many other fruits. Thank you very much for your attention, and we'll go from there. Thank you very much.